In this video, I'm going to model a strategy known as partial subtraction. It's an alternate strategy for teaching students division. It is similar to the standard algorithm. An alternate strategy, by the way, is something other than the standard algorithm when I use that terminology. The standard algorithm is where all kids need to get for the sake of efficiency, especially in division when you're working with large numbers. Anything but the standard algorithm will become clunky, inefficient, and potentially error-ridden. But with smaller numbers and when you're introducing division and really trying to focus on what's happening when they're dividing numbers, in other words, one thing they're doing is they're forming groups, and I'll use that language as I work through this strategy. I don't think in a lot of textbooks the language I'm going to use is necessarily infused into the strategy, but I think it's important to use grouping language as you work the strategy. But anyway, it shows it's really a better way of revealing conceptually what's going on when students divide. Although there are some potential misconceptions that I'll point out. Just in the term subtraction, I think creates potential misconceptions, so you may want to reword this strategy. It's one of the common misconceptions I think with division is that students view it as subtraction. Like when they divide 15 by 3, the answer is 5, and they think that's what you end up with is 5 items and the other 10 disappear. It's not the case. When you're dividing, you're finding out of a group of 15, if I divide it into 3 groups, how much is in each group. So this 5 tells you, pardon my penmanship, how many items are in each group. The 15 are still there, they're just spread out into 3 groups. Watch the video on division big ideas and that'll explain that better. So to use the term subtraction, see, because when they subtract 15 minus 10, that 10 does go away. In problem solving, that's like we have $15, we're spending 10 are gone, so you're only left with 5. But in division, 15 divided by 3, the answer is 5, means something entirely different as it applies to problem solving down the road. So potential misconception in the title of that strategy, but that's what I see it named, so I'm going to use that. It works like this. So I'm going to start taking items away. So I have a set of 84. This is important terminology. I have a set of 84 items, and I need to break it up into 3 groups. Now drawing 3 groups and dividing the 84 items is really inefficient, so we need a better way. So let's start by partial subtraction. We can remove just as many items as we want at a time. So we're going to use common multiples of 3. Like I know 3 times 10 is 30. So I can take that many out, and I have 54 remaining. So I've divvied up 30 items into 3 different groups, and so each group now has 10 items apiece. Now this terminology could be confusing at first as you're teaching them the algorithms, but stay with it, just use it over and over again, and I think they'll begin to see. So now I could go by 10 again and take out 30 more items, because that's an easy thing for me to figure in my head. 3 times 10 is 30. So now I'm left with 24. By now, I've taken out 30, and then I took out 30 more. So I've divvied up those 30, and I now have 20 items in each group. So if I had my circles down here, I'd have 20 items spread out. And by now they may recognize the fact 3 times 8 is 24, and they're done with it. So they've divvied them all up, and see my answer now is, in each group then, I have 28 items in each group. And that's where partial subtraction comes in. Of course, that's not the way you would work the standard algorithm, but it's not dissimilar to it either. It's going to take a little bit longer, but it's a little bit easier way for students to see what's happening, and it also draws their eye on what they're doing when they take these 10, when they end up with these 10 items here and they take 30 out. By taking these 30, divvying them up into 3 groups, I have 10. Now 30 more, 10 more, 24, now 8 more go into each group, and I have 28 total in the end. I'll demo a bigger one because it works good for it works just as well for multi-digit division. This one will have a remainder, just so you know, because that plays out really nicely also. And these strategies are a good way to introduce remainders. So I'm going to start the same way I did before. I've got to find out I've got 362 items. Use this terminology. I'm going to divide them equally amongst 16 groups. So I don't want to draw 16 circles, count out 362 counters, and divvy them up. So I need a more efficient way. So I just start with what's similar. And this, of course, is going to be a much higher cognitive lift for students. So this is several days down the road from from the problem I just demonstrated. But easy enough still is, if I multiply 16 times 10, I get 160, and I can take 160 items out, and I've grouped 160 of them, and in 16 groups they each have 10 items. So 2, 0, 2. So I've already taken care of, I've counted out 160 of the counters, I've divvied them up into the 16 groups, and I have 202 left. Right now I have 10 in each group. Let's go again. Well, that's an easy enough route to go again. I can go another 160, and I end up with 42 remaining now. And now I've counted out 160 more, and I have 10, 20 items in each of my 16 groups. There's 42 remaining that I still need to count out. And so that now they may start going by 16, they may just start going by 1. By 1, subtract 16, by 1, subtract 16, or they may recognize that. They may start trying things and say I can go by 2. And 16 times 2 we know is 32. So I have 10 remaining. So I've divvied up, I've spread out 160 more, and now 32 more of my 362. There are 10 remaining, and I have 10, 22 in each of the 16 groups. Again, there's a lot going on here, so you want to model this frequently, have students do several problems, and use the terminology. So and that's how learning happens. Just have to do it over and over again until they get it. And now I'm asking myself the question, will 16 go into 10? And it won't. So I can't spread these out equally among 16 groups. So my answer then is, depending on what grade you're in, it's 22, remainder 16. That's where you'd start when you're learning division, is with the big remainder. Of course, eventually you can use this strategy to now introduce fractions through remainders, but that's a bit further down the road from this particular point in time in their math learning careers. So that's partial subtraction. Again, make sure you're using the language of grouping. So I have 362 items that I'm going to put in 16 different groups. Now I just start divvying up the 362 items a little bit at a time. That's where the partial subtraction comes into play. Warning on misconception is the term subtraction, because we're not subtracting. None of this goes away. In the end, in this final answer, we have 22 groups of 16. And I actually have a intervention where I make the students write it out like that to reinforce that. It's 22 groups of 16, so there's more than 22. I wrote that backwards. There's 16 groups of 22 items, so there's more than 16, or there's more than 22. There's way more. There's 16 groups of 22, which they know by now. If they multiply that, it's a large group. And in this case, there's a remainder of 10 items that we weren't able to put anywhere.